Hello, my name is Dongho and I'm from the University of Paris-Saclay in France. And I'm going to present our work on concrete categorical model of quantum circuit description language with measurement. This is a collaborative work with Valentin, Perrelle, Benoît, Valiron, who are my supervisors at the CEA, Central Super League, and LMS, and with Zhao Su, who was a postdoc at the LMS. Our work is based on a QRM model of quantum computation. It has two parts. First, classical computer does a classical computation, and it creates a quantum process which is sent to quantum coprocessor. And then quantum coprocessor simulates the quantum process and returns the classical data to the classical computer, which is obtained by measurement on the quantum state. And one implication of this model is that quantum computation can be statistical set of quantum computation. And there are several quantum circuit description languages based on QRM model out there. First, Clipper is an expressive high-order programming language embedded into Haskell, and it has been used to implement various quantum algorithms. However, depending on Haskell's type system, it lacks type system for quantum data. And second, Quire is a general circuit description language embedded into Coq. Using Coq's logic, various quantum algorithms can be implemented and can be analyzed using in Coq. However, although the proofs can be automatized using tactics, it is not straightforward how to scale it up to a realistic quantum program. And in both languages, program constructs circuits using classical computation, and we can also run them on quantum coprocessor. And also classical data is transferred to the classical host by measurement on quantum states. And the last thing is called dynamic lifting, which is formally the information transfer from the quantum coprocessor to classical host, and the information is used in circuit construction. So for example, let's look at the expression below, where the qubit Vc is measured, and the outcome is stored in the pair of Boolean and a qubit denoted by B and Vc, and depending on the Boolean B, it creates different quantum circuits. So quantum circuit construction in the classical host is now dependent on the result of a measurement. Clipper and Quire implement dynamic lifting, however, they don't give an explicit formalization of its semantics. Therefore, in our work, we have two questions. First, how to formalize dynamic lifting in operational semantics? And second, what is categorical representation of dynamic lifting for a circuit description language? And our work is based on the fact that dynamic lifting generates multiple control flows in classical computation, each of which is interpreted as a quantum channel. Now let me introduce how we formalize dynamic lifting in our operational semantics. In order to do that, we define a formal language called prototypical L, where we extend the prototypical language with quantum channel constant and a branching term. In order to define the quantum channel constant, we define the algebraic structure of quantum channel. So QC arc is an abstract structure of quantum channel which represent quantum circuits with tree-shaped control flow with measurement. And you can see that we introduce a constructor for measurement, which is followed by quantum channel object called Q1 and Q2. Since not all quantum channel objects are valid, we introduce a relation called ST to formally describe what's the valid composition of quantum channel objects with different inputs and outputs. And then we define a quantum channel constant for the language, which is a tuple of a object Q and a term M. And we also define a type for the quantum channel constant, which is called Q-chain. Now we define the language for the quantum channel description language and a linear and nonlinear type system. Since quantum computation containing dynamic lists may reduce to different values depending on the results of measurement, we introduce a branching term to describe non-deterministic computation. Another language has two parts. The non-branching part is the same as the prototypical language, where we just substitute the quantum circuit constant with quantum channel constant, and the branching part is defined as either non-branching term or a pair of branching terms. And then we define a linear and nonlinear type system, which ensures that quantum variables are used exactly once in each branch of control flow. The type system consists of a typing judgment and a set of typing derivation rules. Now, the typing rules ensure that all terms of a branching term share the same type. And for example, we show the two typing derivation rules for quantum construction operators box and unbox as follows. And then we define the operational semantics for the language. Operational semantics is formalized as a circuit buffering abstract machine which buffers quantum channel while reducing the term. The abstract machine consists of a configuration and a transition function or a reduction rules defined over the configuration. And configuration is represented by a pair of a quantum channel object Q and a branching term M. And we represent graphically configuration with a green box, which represents a quantum channel, and a set of squared box, which represents a branching term, which is linked to the output of the quantum channel object. And the edges represent bundles of wires, which is either multiple wires or empty wire. And the reduction takes place in each branch of the branching term. And now I'd like to give you some example of our semantics. First of all, the measurement is formalized as follows. We define a constant called mid, which is a term of type function from qubit to a tensor of Boolean in qubit. And this constant applied to a qubit has a two-former behavior. On the classical computation side, it creates a state for each outcome. And on the quantum channel side, it adds a measurement gate to the circuit. And from our operational semantics, the measurement applied to a qubit X is reduced to a quantum channel with measurement, which is linked to a branching term, which is shown in the figure 3. And then returning to the expression from the equation 1, where the qubit VC is measured and the different circuits are constructed depending on the measurement. And despite a simple structure, the term does not correspond to a circuit because of the classical control. In our operational semantics, this term reduces to a quantum channel in a branching term, which is shown in figure 4, where the quantum channel has a non-trivial structure. And we prove for the language a type safety property, which intuitively says that our well-type configuration reduces to a value. In order to formally state the type safety property, we need to extend the typing judgment for the configuration. And then the type safety for prototypical error consists of two lemmas: subject reduction, which says that a type is preserved over the reduction rule from the operational semantics, and the progress lemma, which says that a well-typed configuration is a value or it reduces to some other configuration. And note that in our language, every term terminates. Now I would like to explain how we formalize dynamic listing in our categorical model. We build a categorical model based on several other works. First of all, our model is highly based on Prototypical M by Francisco Rios and Peter Selinger. They build a categorical model for parameterized circuits. To explain, symmetric monoidal category is used as a model of graphical languages for circuits, which consist of boxes and strings. And they build a symmetric monoidal closed category based on compilation for the higher order quantum circuits, which means that they have objects for quantum circuits. And then the Coproduct compilation gives a model of parameterized circuits. And their model is also based on Valentin's linear and nonlinear category, which allows to interpret the exponential type and also the interaction between the classical host and quantum coprocessor, namely box and on-box operator. Moreover, our model is also based on Moji's categorical interpretation of side effects. In particular, we define a branching monad to incorporate the non-deterministic computation introduced by dynamic listing. To define a concrete categorical model, we formally define a diagram. Diagram is a directed graph composed of multiple types of nodes and marked edges. The mark for edge is defined as follows. There is a unit mark I and Q for qubit. We can have a tensor product marks and box plus composition of a family of marks, and then the dual of a mark. There are also different types of nodes, which are illustrated in figure 5. The elementary nodes consist of the single nodes, which of different names, which can have a different input and output. And then one can compose a family of diagrams using box nodes within box nodes. And the diagram comes with an equivalence relation, which is a set of coherent substitution rules for diagrams. From the definition of diagrams, we can build a category M bar, which is formally defined with the following data. The objects are lists of marks, and the morphisms are the equivalence class of diagrams. And we can show the M bar is symmetric monoidal with the unit I with the empty list, and the tensor product defined for the object as a concatenation of lists, and for morphism as a juxtaposition of diagrams. And we can also define an internal home by using the dual of marks and concatenation of lists. Also, we can define a product by using the box plus composition of marks. And then the bit type in Clipper can be defined as the object I box plus I within the category and bar. And we define a coproduct completion of the category with the model families of circuits. The coproduct completion and bar of symmetric monoidal cos category, which was introduced just before, is defined as follows. The objects are represented as a pair of a set X and a family of object AX in M bar. The morphism is then represented as a pair of a set function F0 and a family of morphism Fx in M bar. And as shown in Prototype M paper, the M bar is symmetric monoidal closed and it features products and coproducts. The monoidal unit is defined as a pair of singleton set of empty set and the unit from M bar, and the tensor product is defined as a Cartesian product from set and the tensor product from M bar. And we can also define the internal home as a pair of set functions and a family of internal homes in M bar. And then on top of that, we define a monad for branching computation. In order to do that, we define a strong monoidal functor F for non-deterministic branching effect. It is defined for an object A as a pair of a set of multi-sets of X in the family of products of object AX, where X is an element of the multiset L. And for the morphism F, F of F is defined as a pair of a set function from the set of multiset to the set of multiset and the corresponding family of morphisms in M bar. And the details can be found in the paper. And based on this monoidal functor, we can build a monad together with a unit and multiplication. And it allows us to define a classically category where we interpret the language. And as an example, we can interpret the listing in our classically category. And to explain, there are two notions of Boolean in our categorical model, which are state Boolean and parameter Boolean. In our context, listing can be interpreted as a morphism from state Boolean to a parameter Boolean, which intuitively means that we extract the branching structure which resides in quantum channel to the branching structure that we can use in classical computation. And thanks to the monad, we can define listing as a morphism in the classically category. More generally, we can interpret the language prototype Perrelle within the classically category and bar F, where the types are mapped to objects and the type judgments are mapped to the morphism. And the typing derivation rules give a specific construction of the morphism. This interpretation is based on the interpretation of type, which is shown below. And note that the P and B are the functors that come from the adjunctions from the Valentin's linear and nonlinear category. And one remark is the home set from the Clay-Slick category is isomorphic to the home set from M bar whenever A and B are state objects. And it means that the Q-chain types correspond to the morphisms of the category M bar, which are quantum channels. And we interpret the type configuration as a composition of the interpretation of Q followed by the interpretation of the term M. As an example, we show the categorical interpretation of the term from the equation 1. And it can be represented as a following morphism. F0 is a set function which maps the set of empty set into a multiset of pair of empty sets. And F is a morphism in M bar, which is shown in figure 6. The left-hand side of the figure shows a measurement applied to the VC, and the right-hand side represents the if-then-else statement, which depends on the measurement outcome. And finally, we show the soundness of the categorical model, which states that the categorical interpretation of the typing derivation is preserved over the reduction from the operational semantics. However, in our type system, there can be multiple typing derivations, so we weaken this statement and show the following Soundness theorem. For any configuration and its reduct, if it has a type A, then for any typing derivation pi 1, there exists a typing derivation pi 2 for the reduct, such that the interpretation of pi 1 and pi 2 are equivalent. And note that the soundness theorem from the operational semantics infers that the reduct has also the type A. And one remark is the denotation of closed term of basic types is independent from the choice of typing derivation, because for the basic types, the values have a unique type derivation. And it leads us to the following corollary, which says that all the typing derivations of a closed term of basic type share the same interpretation. To summarize, we have defined a simple language extending proto-Clipper linear and non-linear type system. Formalizes semantics of dynamic listing and non-trivial control flows generated by measurements in quantum circuit construction. And we showed safety property of operational semantics and the soundness of categorical semantics. There can be several remarks. First of all, the model is closely related to the models of intuitionistic linear logic. And secondly, it can also be considered as an extension of diagrammatic languages for quantum processes. And the branching monad follows Clipper's operational semantics, which is encoded in Haskell's type system. We answer an open question in the community, which is finding a categorical representation of dynamic circuit description language.